The Unified Extensible Firmware Interface, UEFI, is a standard for the firmware architecture of computing platforms, initializing before the operating system upon powering on a computer. Common implementations are AMI Aptio, Phoenix Secure Core, Tianocore EDK2, and Inside H2O. UEFI supersedes the BIOS found in IBM PC-compatible computers, providing compatibility with BIOS through CSM booting. Unlike the proprietary BIOS, UEFI is an open standard overseen by an industry consortium, being maintained and developed by the UEFI Forum, initially based on Intel's Extensible Firmware Interface, EFI specification. The motivation for EFI stemmed from limitations encountered during the inception of Intel HP Itanium systems in the mid-1990s, aiming to alleviate constraints faced by server platforms targeted by Itanium. Originally known as the Intel Boot Initiative, it evolved into the Extensible Firmware Interface, EFI, and later the UEFI standard. Intel transitioned the EFI specification to the UEFI Forum in 2005, and subsequent versions have been collectively developed under UEFI. UEFI is agnostic of platform and programming language, with C commonly used for its reference implementation, Tianocore EDKey. UEFI's evolution introduced cryptographic and security features in version 2.0, followed by network authentication and a user interface architecture in version 2.1. In recent years, ARM established certification programs like ARM Server Ready and ARM System Ready, mandating firmware compliance with standards like UEFI for various server and IoT environments. Additionally, initiatives such as Project Mu by Microsoft have emerged, aiming to enhance firmware development practices. The latest iteration of the UEFI specification, version 2.11, was released in December 2024. UEFI supports processor architectures that are 32-bit or higher, with a preference for processors that have a little endian mode. The official documentation for the UEFI specification version 2.11 includes processor architectures such as x86, IA32, x86, 64, Itanium, IA64, ARM, Arch32, Arch64, RISC-V, 32-bit, 64-bit, 128-bit, and LungArch, 32-bit, 64-bit. Unofficial UEFI support is also in the works for PowerPC 64 and MetPS. UEFI firmware strictly executes applications that match its bit width, even if the processor supports different modes. Some lower-end computers have been known to ship with 32-bit UEFI firmware on 64-bit CPUs. Once a UEFI application finishes boot services, it can alter the processor execution mode, but must revert briefly for calling runtime services due to mode restrictions. When it comes to disk device compatibility, UEFI can work with the Good Partition Table, GPT scheme, which surpasses the limitations of the Master Boot Record, MBR. GPT allows for significantly larger disk and partition sizes compared to MBR, supporting up to 8 ZB with 512-byte sectors. UEFI solely supports FAT12 1632 partitions on GPT or MBR disks and El Torito formatted optical disks. GPT, while part of the UEFI standard, can also be utilized by BIOS PCs for booting operating systems. Linux supports GPT by enabling Config-FI partition during kernel configuration, allowing recognition and usage of GPT disks post-firmware handover. Additionally, Linux can function with GPT disks on BIOS-based systems, referred to as BIOS GPT setups. UEFI systems have the capability to access and boot from GPT disks directly, enabling the use of UEFI boot techniques with the creation of an EFI system partition, ESP, containing essential UEFI applications like bootloaders and operating system kernels. For backward compatibility, some UEFI implementations support booting from MBR partition disks through the Compatibility Support Module, CSM, providing legacy BIOS support. Windows operating systems from Vista onwards can also boot from GPT disks larger than 2 TB. EFI services are divided into boot services available before firmware ownership transfer and runtime services accessible post-transfer. Some services include Graphics Output Protocol, GOP, for runtime graphic access, UEFI memory map services, time services, and application support. UEFI allows for running UEFI applications like bootloaders independently, interacting through protocols and device drivers with a focus on interoperability and efficient functioning. The EFI system partition, ESP, is a crucial partition used in computers adhering to the UEFI specification. It serves as a storage device for UEFI applications and necessary files like operating system bootloaders. The ESP supports various partition table schemes such as MBR, GPT, and El Torito volumes on optical disks. Within ESPs, UEFI outlines a specific version of the FAT file system, encompassing FAT32, FAT16, and FAT12. Additionally, the ESP reserves space for a boot sector to maintain backward BIOS compatibility. In contrast to legacy PC BIOS, UEFI employs a boot manager instead of boot sectors. This boot manager, defined by the UEFI specification, checks the boot configuration upon computer startup and executes the specified OS bootloader or operating system kernel based on the settings. This configuration is stored in NVRAM variables, indicating file system paths to OS loaders or kernels. UEFI can automatically detect OS bootloaders, facilitating easy booting from removable devices like USB flash drives. Booting UEFI systems from GPT partition disks is commonly referred to as UEFI GPT booting. Some UEFI firmware implementations may switch to BIOS-based CSM booting on MBR partition disks, hindering UEFI booting from ESPs on such disks, leading to what is known as UEFI MBR. The Compatibility Support Module, CSM, allows legacy BIOS booting from MBR disks, ensuring backward compatibility. Additionally, UEFI supports network booting via the Pre-Boot Execution Environment, PXE, allowing booting over a network using various protocols like DHCP, TFTP, and ISCSI. Secure Boot is a UEFI protocol that enhances security during the boot process by only loading signed UEFI drivers or OS bootloaders. Secure Boot can be enabled in different modes, such as user mode and custom mode, allowing flexibility in managing digital signatures. This feature is supported by various Windows versions, VMware vSphere, and several Linux distributions. UEFI provides a shell environment enabling the execution of UEFI applications and bootloaders. The UEFI shell offers commands for system information retrieval, manipulating boot manager variables, running partitioning programs, and more. Extensions to UEFI can be loaded from non-volatile storage devices, adding functionalities to the standard UEFI firmware. UEFI Capsule defines a firmware update interface, promoting modern and secure firmware updates. In summary, UEFI serves as a modern replacement for BIOS, initializing system hardware components and managing the boot process efficiently. The security phase serves as the initial stage of the UEFI boot process, potentially containing platform-specific binary code like Intel ME, AMD PSP, or CPU microcode. It is crafted with minimal assembly language code tailored for the specific architecture, setting up temporary memory, usually CPU cache as RAM or SoC on-chip SRAM, and acting as the foundational trust point by validating PEI integrity. Moreover, the security phase handles tasks such as initializing temporary memory for the subsequent stage, PEI, and relaying crucial system details like temporary memory location and size, stack location and size, along with platform state information. The pre-EFI initialization, PEI phase, represents the following step in the UEFI boot sequence, employing a dependency-aware dispatcher to load and execute PEI modules, PEIMs, responsible for early hardware setup like main memory initialization and firmware recovery functions. Not only does PEI dictate the current boot mode discovery, but also oversees various ACPI S3 operations, handling tasks such as registering hardware to a pre-sleep state in the case of ACPI S3 resumption. Furthermore, PEI creation involves establishing memory data structures and initializing default values, consisting of components like PEI Foundation, PEIMs, and PPI. After the handoff from the security phase, the PEI Foundation shoulders the platform responsibilities, ensuring successful PEIM dispatch, initializing permanent memory, RAM, and transitioning control to the subsequent stage, DXE. Responsibilities also include enabling communication among PEIMs through PPIs. The PEI dispatcher is accountable for invoking PIMs and orchestrating their dependencies. PIMs, essential PEI drivers from various vendors, focus on single hardware component initialization tasks, ensuring each carries out its designated function diligently. The PIMs to PIMs interfaces comprise good pointer pairs, aiding the discovery of PPIs by PIMs via PEI services. The driver execution environment, DXE, the subsequent stage, involves C modules and a dependency-aware dispatcher for CPU, chipset, mainboard, and I/O device initialization, while the boot device select, BDS phase within DXE oversees boot device initialization and execution of UEFI drivers or option ROMs based on NVRAM-defined variables. Following BDS is the transient system load, TSL stage, bridging the gap between boot device selection and OS handoff, allowing entry to a UEFI shell or execution of UEFI applications like OS bootloaders. Finally, runtime, RT, marks the transition to the operating system post-exit boot services, with UEFI-compatible OS in charge of unloading unnecessary firmware and executing runtime services. The EDK2 Application Development Kit, EADK, enables the use of standard C library functions in UEFI applications and is accessible for download from Intel's Tiano Core UDK EDK2 SourceForge project. An illustration of this is the port of the Python interpreter to a UEFI application facilitated by the EADK. The development transition to GitHub post UDK 2015. A basic Hello World C program written with EADK shares resemblance to a typical C program, exemplified by a code snippet that includes UEFI.h, library UEFI-lib.h, and library shell sentrylib, among others, followed by an fstatus FEAPI shell app main function that prints Hello World on the screen. There have been critiques of UEFI by digital rights activists like Ronald G. Minnick and Cory Doctorow, contending that UEFI restricts user control over computers. Notably, UEFI does not address the long-standing issue of needing separate drivers for firmware and operating systems for most hardware. The open-source Tiano Core project also offers UEFIs, lacking certain specialized firmware drivers and modules for initializing chipset functions. Tiano Core serves as one of many payload choices for coreboot. The development of coreboot hinges on collaboration with chipset manufacturers to provide essential specifications for developing initialization drivers. One aspect of UEFI that garnered attention is secure boot. Microsoft mandated that devices certified for Windows 8 must have its public key enrolled with secure boot enabled, making UEFI a necessity for such systems. Critics contended that this move aimed to impede the installation of alternative operating systems like Linux. Various Linux distributions devised implementations for secure boot, with Ubuntu using shim pre-configured with Canonical's key, allowing unsigned kernels to load. Fedora requires both the kernel and modules to be signed. The ongoing debate includes technical, legal, and practical hurdles in supporting secure boot on Linux systems. Furthermore, technical issues linked to UEFI firmware have surfaced, such as Lenovo models with secure boot permitting only specific executables to load, causing operational constraints. Toshiba laptops encountered problems due to missing certificates necessary for secure boot functionality. Samsung laptops faced issues post-Linux installation in UEFI mode, eventually discovered to be triggered by an overflow of UEFI variables in memory. These instances underscore the complexities and challenges associated with UEFI firmware implementations.